let's understand how we can find the time period of oscillations or frequency of oscillations in SHM questions. So there are few steps we adhere to that. First step is you displace the body from its mean position by a very small distance y. Understand that this is only for the linear SHMs where the body is executing SHM in a straight line. We can also have an angular SHM like a pendulum which is moving in an arc. We'll come to that later on. Right now we are just talking about the linear SHMs. So over here the first step is you displace the body from its mean position by a small distance x or y. Over here we have taken it as y. Once it is displaced, then somehow it will have a tendency to reach back to its mean position. That is, we find the restoring force. Once we find the restoring force, we put it is equal to m into a, that is mass into acceleration. If the acceleration comes out to be minus y, that is minus of displacement, this is necessary and sufficient condition to prove that this motion is SHM. Once this is SHM, we can very safely use the formula which we have just derived, that is t is equal to 2 pi y by a. Now let's see how we use it. Over here we take a simple case. Once again, this is mass m attached to a spring of spring constant k, and this is a frictionless surface, and we wish to find that is what is the time period for these oscillations. So what we do is first we displace it, slightly displace it from a mean position by distance y. Once it is displaced from here to here, then obviously that is we have done the first step. So if it is moved by distance y, so there is also stretch in this also, spring also, that is by y it is stretched, and we know F is equal to minus ky in spring, that is the restoring force is k into y where k is spring constant. So the spring will pull this body towards its mean position by a force ky. Right, ky. So ky is equal to ma. So when the body is pulled from its mean position by distance y, this spring gets stretched, and as a result we know F is equal to minus ky. This is a force, restoring force, which is generated in the spring when its natural length changes by y, that is y stands for deformation. Be it elongation or compression, F is equal to ky, where y stands for deformation. So when it is pulled like this, then the restoring force ky is in this direction. So ky is equal to ma. So A comes out to be k by m into y. So now k stands for spring constant, and for any spring k is constant. M, mass of this block, that is also constant. So acceleration is proportional to y. If we remove the equality sign, this is constant, so this becomes acceleration is proportional to y. Also the displacement is in this direction, restoring force is in this direction, so obviously acceleration is also in this direction. So it means displacement and acceleration, they are opposite directed. This is a necessary and sufficient condition to prove that this motion is SHM. So if this motion is SHM, then we can use this, that is t is equal to 2 pi y by a. So t comes out to be 2 pi over here, a is equal to k by my. So y by a, so y by a stands for m by k. So we can put it over here in this. So this comes out to be y by a comes out to be m by k. So m by k, this is the time period for this body of mass m, which is attached to spring k on a frictionless surface. When this is going to execute SHM, its time period is going to be like this, and linear frequency is going to be 1 by t. You can put it over here and you can find this frequency in cycle per second or hertz or simply per second.